So, good morning, students. We are discussing the nucleophysics and analytical techniques of series of lectures. In in the previous classes, we have discussed the material characterization technique. In the previous class, we have discussed about the phase contrast microscopy and electron microscopy and scanning electron microscope, and also transfer. Them also we have discussed that is. Uh, so today we are going to discuss about some of the thermal analysis techniques which are gravitrometric analysis and DSC and DTA. Let us go into the topic. I will share the screen. In the earlier class, we have discussed some other techniques, the SEM10 and EM, that is electron microscope, and scanning electron microscope and transverse electron microscope. So now today we are going to discuss about the thermogravimetric gravimetric analysis, that is TGA, we call it as TGA. Myself do believe. So in this topic we are going to cover this today's lecture. We are going to cover these topics like thermogravimetric analysis, differential scattering, calorimetry. Okay, these are the two topics we are going to discuss today. So what is thermal analysis actually? So thermal analysis is a branch of material science and a group of analysis which study the property of material when the change it with the change when the change in temperature. So actually thermal analysis is a branch of material science. Okay, so it is a material science branch and which studies the properties of materials with the change in temperature. Okay, as the temperature changes, we will try to study the properties of that sample or material which we want to find. Okay, in this technique, mass of substance is measured as form of temperature. So in this thermal analysis techniques, what we will do the mass of the substance will be measured as a form of temperature. Okay, when it is subjected to controlled temperature, we subject it to controlled temperature and we will try to find the mass of the substance by measure of temperature. Okay, so there are types of thermal analysis. There are some types of thermal analysis, that is thermogravimetric analysis, that is TGA or PG we will call thermogravimetric analysis, differential scanning calorimetry. This is one of the technique, and derivative thermogravimetry and differential thermal analysis. These are the four techniques. In these four techniques, we are going to study thermogravimetric analysis and differential scanning calorimetry. Okay, these are the two topics we are going to cover today. So next, if you see the contents in the thermal analysis, thermogravimetric technique. Introduction, we will go into discuss and types, principle, PGA curve, instrumentation, factors affecting results, advantages, limitations. These are the topics we are going to cover. So to go into thermogravimetric analysis, TGA, thermogravimetric analysis or thermal gravimetric analysis, TGA, is a method of thermal analysis in which the mass of a sample is measured over time as the temperature changes. So, as the temperature changes, we try to find the mass of the sample. Try to find the mass of the sample as the time changes and with the temperature changing. Okay, so in this, what we will do in this thermal analysis, thermogravimetric analysis, we will try to find the mass of the sample. As the time changes, temperature changes. So with the change of temperature, with the time, we'll try to find the mass of the sample, how the temperature is changing based on that. Okay. This measurement provides information about the physical phenomena. So this measurement, this diametric analysis measurement provides information about the physical phenomena such as phase transitions, absorption and desorption, as well as chemical phenomena including absorptions, thermal decomposition, and solid gas reactions. Example, oxidation or reduction. So by using this PGA, it gives the information about the physical phenomena. What are the physical phenomena which we can measure the phase transition, how the phase transition of this sample is occurring, and how much it is absorbing, how much it is desorption is happening, and also we can measure the chemical phenomena also by using this TGA. Those are chemisabsorptions, thermal decomposition, how the thermally decomposing, and solid gas reactions. Okay. So three types of gravimetry will be there. So in this, if you see what are the three types of gravimetry, first one is isothermal or static thermogravimetry. This is the first type of TGA, isothermal or static thermogravimetry. And next one is quasi-static thermogravimetry. And dynamic third one is dynamic thermogravimetry. So dynamic thermogravimetry. If you see for the first one, isothermal or static thermogravimetry, in this technique, the sample weight is recorded as a function of time at constant temperature. So in the isothermal, static thermogravimetry, isothermal or static means what? Where we will keep the temperature constant. So we try to keep the temperature constant and we try to find the weight of the sample. In this technique, the sample weight is recorded as a function of time. So as a function of time, we try to find the mass, the weight of the sample by by keeping the temperature constant. Okay. This is about isothermal or static thermogravimetry. Okay. Quasi-static thermogravimetry. In this technique, the sample is heated to constant weight at each of series of increasing temperatures. So in the quasi-static thermogravimetry, what you will do? So the sample will be heated, okay? Constant weight. Up to a constant weight, the sample will be heated. Each series of increasing temperature. In each series, the temperatures will be increased, and the weight of the sample will be constant. Okay. This is quasi-static thermogravimetry. Third one is dynamic thermogravimetry. In this technique, the sample is heated in an environment whose temperature is changing predetermined manner. Whose temperature is changing predetermined manner, generally at linear rate. Generally at linear rate. This type is generally used. So dynamic thermogravimetry, in the dynamic thermogravimetry technique, the sample will be heated. Okay, the sample will be heated and temperature will be changing. Okay, the temperature changing linearly as the temper as it is heated as it is heated gradually. It will the temperature also changes linear rate. Okay, so in this type is generally. So this is the method we will use actually. No. So if you see the TGA curve, the, sorry, if you go for the principle of this TGA, on what principle is the TGA curve, TGA technique is used is this one. In thermogravimetric analysis, the sample is heated in a given environment, air, nitrogen, oxygen, helium, argon, etc. These are the environment gases, isn't it? So the sample will be heated at controlled rate. So at controlled rate, the sample will be heated. The change in weight of the substance is recorded as a function of temperature or time. So, so what we will do, the principle is that the sample will be heated in the given environment at a controlled rate. Okay, the sample is heated, and the weight of the substance, we will record the weight of the substance as a function of time or else as a function of temperature. Okay. So this is the principle of PGA. The temperature is increased at constant rate. The temperature will be increased at constant rate for a known initial weight of the substance. If the sample is known, then sorry, the temperature is increased at constant rate of for known initial weight of the substance. As a sample weight is known, we will increase the temperature at a constant rate, and the changes in the weights are recorded as a function of temperature. As the if the temperature is increased, if you consider at a temperature of 40 degrees, some of the samples weight is, let us take 4 grams. If I consider at 60 temperature, the sample's weight is reduced to 3.8 grams or 3.7 grams. You can easily determine the weight of the sample with the temperature. We can draw the sample with the temperature curve, right? So here, the initial weight of the substance, as the temperature is increased at constant rate for known initial weight of the substance, the changes in weights are recorded. So there is a changes will be seen in the changes will be seen in the weights of the sample, that will be recorded as a function of temperature or as a function of time interval. How much time it is taking to decrease its weights mm, or disintegrate into uh, lesser weights. Okay. This plot of weight change against temperature is called thermogravimetric curve. So the plot which we draw between this change in temperature to the weight. As the temperature changes, the weight of the substance also changes. So we will draw the graph between these two variables, that is temperature and weight. So this plot is called thermogravimetric curve. Okay, what we call, we'll call it as thermogravimetric curve or thermogram. We will call it as thermogram. This is the basic principle of TGA. So this will be the basic principle. What we will do for the TGA, we actually, so we will heat the sample in the given environment, and we will weight the substance with in the function of time or temperature. As the change in temperature, as the temperature changes, the weight of the sample changes, and we'll try to plot the change of the weight to the temperature, and with that plotting of weight against the temperature is called thermogravimetric curve of thermogram. So this is the principle. Okay, this is the thermogravimetric analysis curve. So if you see, the instrument used for thermogravimetry is a programmed precision balance for rise in temperature known as thermobalance. So we use the instrument for the programmed precision of balance, actually for measuring of the uh, rise in temperature. So for the mass, we will use a uh, instrument called thermogravimetry, which is programmed precision balance for rise in temperature known as thermobalance. We will use as thermobalance. We will use the thermobalance to know the values. Okay. Results are displayed by a plot of mass. So the results will be in the thermobalance. The results are displayed by a plot of mass change versus temperature or time. Okay. The results will be displayed the plot against the mass and the temperature versus temperature or time, and are known as thermogravimetric curves or PG curves. So these type of curves are called gravimetric curves. Okay. So in this PGA curve, what we are doing? making we are increasing the sample's temperature, and we are decreasing mass of the substance, mass of the sample, isn't it? Or and hence we are finding the mass of the sample as the temperature changes or time changes. Okay, so we are plotting the graph between mass and temperature, and this graph, this plotting of this graph is called PGA curve. Okay. So PG curves are normally plotted with the mass change dm in percentage on the y-axis and temperature or time on the x-axis. So as we see here in this plot, we are seeing the on the y-axis we are seeing the mass, on the x-axis we can see the temperature, right? So this is plot like this. Okay, there are two temperatures in the reaction: Ti, procedural decomposition temperature, and Tf, final temperature. So representing the lowest temperature at which the once onset mass onset mass change is seen, and the lowest temperature at which process has been completed respectively. So we can observe two temperatures here, that is Ti and Tf. Proceed Ti is what? Procedural decomposition temperature, actually. Procedural decomposition temperature. And Tf is what? Final temperature. So Tf will be the final temperature. Tf is what? This is a final temperature. This is the procedural uh, procedural decomposition temperature. At least the mass will be decomposed at the temperature with the mass is decomposed, and it is maintained at some point. Okay, the mass will be constant after Tf. Okay, at Ti, it is initiating to disintegrate, or it is changing its mass up to some point of temperature, that is Tf. Okay, this is the final temperature. At least the mass won't change again. Okay. The reaction temperature and interval Tf minus Ti depend on experimental condition. Therefore, they do not have any fixed value. So the reaction temperature, the reaction temperature and this interval between that final temperature and initial temperature. So this difference between final temperature and initial temperature and the reaction temperature will depend on the experimental condition, how the conditions of the experiments are, how the surroundings of that experiment is there, how the experimental conditions are there, how much the pressure is there, how much uh, sample size is there. By that, it will be by on that it will be become there. Therefore, they do not have any fixed value. So these do not have any fixed value. These temperatures will not be have any fixed values. Okay. So the example of PGA curve for AG and voltage. Even A is here actually, B is here, C to D. This graph is actually, this is A, here it is B, here it is C, here it is D. Okay. So the horizontal portion you see for the AG and silver nitrate, this is the graph between temperature and mass, that is weight to the temperature. AgNO2 is decomposed to Ag plus NO2 plus O2, that is gives rise to Ag silver plus NO2 plus O2. So here, if you see the horizontal portion of the curve indicates that there is no change in weight. So A to B, if you see, there is no change in weight. Okay, the horizontal portion of the curve, first horizontal portion of the curve, it doesn't change with the temperature up to where to B, right? And also from C to D also. So the horizontal portion of the curve indicates there is no change in weight, AB and CD. From A to B and C to D, there is no change in the weight. And the portion BC, and the portion from B to C, indicates that there is a weight change. So as this is coming down, the weight is on the y-axis, It is changing its weight, right? The weight is changing from B to C. How much it is changing from 100 to 50? It is changing, right? So the weight of the substance AgNO3 remains constant to a temperature of 473 degrees. So, so up to 473 degrees of AgNO3 for AgNO3, if you see this one is 400, it is about 450, it is 470, I think. So up to here, the AgNO3 is constant. The weight of the AgNO3, weight of the substance is constant. But after 473 degrees centigrade, what happening? It is thermally, it is thermally becoming unstable and it is losing its weight, isn't it? It is losing its weight from B to C. So the mass of the, if you consider the weight of this sample is 100 and it is becoming, after 473 degrees, is becoming 50. Half of its mass is losing it, which is losing half of its mass. So we can say that this AgNO3 is thermally stable. It will be thermally stable up to after how much degrees? It is thermally stable up to 473 degrees centigrade. Okay. So we can say that this AgNO3, this silver nitrate is thermally stable up to 473 degree centigrade. I hope you understood. This is the flat horizontal curves we can observe from A to B and C to D. These are what actually, there is no change in its weight. There is no change in its weight of the AgNO3. That is 100 and here it is 50 almost. So the change is only in the B to C. B to C where the mass is changing rapidly from B to C as the temperature is changed from as the temperature is increased from 473 above. Okay. So here it is thermally unstable. You can say AgNO3 is unstable. At this temperature, it starts losing its weight, and this indicates that decomposition starts at this temperature. So we can say that at 473 degrees centigrade, the silver nitrate is starting starting to decomposition, and it is decomposed from B to C. Okay, it decomposes to NO2 and O2 and Ag. So silver, oxygen, and nitrous oxide, it has decomposed as like this NO2, O2, and Ag. Okay. The diagram indicates the PGA curve for AgNO3. So this diagram indicates the PGA curve for the AgNO3. I hope you understood this diagram. So here actually from A to B, the weight of AgNO3 is not changing. After 473 degrees centigrade, as the temperature is increased gradually, like 473 degrees centigrade, it is, as it is increased higher temperatures, so higher temperatures, this AgNO3 is rapidly falling and it is decomposing and it is stable at again, it is thermally stable at again 50 grams. So at this point where C to D, it is also, here also it is flat. Okay, here also it is flat. So this is the PGA curve for AgNO3. So the loss in weight continues. The loss in weight continues. The loss in weight continues up to loss in weight continues to 608 degrees centigrade, and beyond this temperature, the weight of the sample up to 608 degrees centigrade, and the beyond this temperature, the weight of the sample remains constant. This is shown by the portion of the curve CD. So the loss in weight continues up to where 608 degrees centigrade, and beyond this temperature, the weight of the sample remains constant. This is shown by the portion CD. So, to 608 degrees, again it will be constant. From there, again it will change its temperature. Okay. So, beyond this temperature, the weight of the sample remains constant. This is for portion of the curve CD. The portion between BC represents the decomposition of silver nitrate. That is, decomposition is complete 608 degrees centigrade, leaving metallic silver as the stable residue. So, up to 608 degrees centigrade, it will be completed, is a decomposed, and it will give the metallic silver of the stable residue. So this is the instrumentation of PGA, that is thermogravimetry analysis instrumentation. You can observe this is the atmospheric control. This is the sample holder here. This is the sample holder, which is connected to recording balance and to the balance control and to a recorder. Here the sample control is sample holder. In this sample holder, we will keep the sample, and this is the furnace, and this is the atmospheric control, and this is the furnace temperature program. This is the these are the temperature sensors. Okay, so here in this TGA, we will see this is the block diagram of TGA actually. So here, this is what furnace. This is the sample holder. In this we will keep the sample, and this furnace will keep the temperature and heat provided to these samples. And this is the atmospheric control. This can control the atmosphere. And this is the furnace temperature program. These are the temperature sensors. We will try to see the apparatus description here. So, instrumentation block diagram of TG. The apparatus required for the TJ analysis are the furnace, which can be heated so that the temperature gives linear with the time. So there will be a furnace which is heated so that the temperatures will get so that the temperature give linear with the time. Or the temperature is increased as the time changes. Okay. Furnace control thermobalance is also will keep the we will be having furnace control thermobalance will be also there. Okay. The furnace control thermobalance will be also there. A known weight of the sample is taken in a crucible C. So in the sample holder, we will take a known weight of sample in crucible C, which is enclosed by a furnace. The furnace F temperature raised slowly. So the furnace F temperature will be raised slowly. The temperature of the sample and the corresponding weight are taken. So what we will do? So we'll take the sample in a crucible actually. So we'll take the sample in a crucible and we will keep it in a furnace, that is in a sample holder in a furnace. So the furnace temperature is raised slowly. As the temperature of the furnace is raised, the temperature of the sample also raises, right? So as the temperature is raised, the temperature of the sample is raised, there will be change in the weight, isn't it? Up to some point there will be change. There may be no change in the weight, but after some time there may be a change in the weight that that are the values of the weight and the temperature are calculated, and we will take the values of those temperature and weight. So first what we will do, we will take the crucible and we will take the sample in the crucible and we will keep it in the uh, sample holder, and we'll try to uh, enclose the furnace so that furnace will raise the temperature of the crucible and the sample. As the sample temperature is increased slowly, there will be change in the weight that are taken as the readings. The readings are taken of the temperature and the weight. Okay. A platinum rhodium thermocouple is used to measure the sample temperature. So there are some uh, temperature sensors are there, right? These temperature sensors are actually this platinum rhodium thermocouples. Okay, thermocouples are the temperature sensors which are used to measure the sample temperature. For the measuring of that sample temperature, we are using this thermocouple. Maximum we will use this platinum rhodium thermocouple. Okay, and the change in weights are found out by finding the beam deflection. So by finding the beam deflection with the weights, uh, we try to find the weight of the sample and on adding a known weight of the pan. So, and the change in weights are found. So the change in weights can be found out by finding the beam deflection on adding a known weight to the pan. So as we are given to the known weight to the pan, we will try to find the what is the loss of weight of the sample. The change in weight are recorded from the beam deflection. So there will be deflection in the beam that can be seen so that the so we can record that beam deflection as a change in weight. Okay. So just now we have seen this instrumentation block diagram. So here the first, second one is the third one is the recorder. So if you see recorder records the change in weight in y-axis and with respect to temperature on the x-axis, we get a thermogram. Just now we have seen the TGA curve on the y-axis. There will be weight change in weight will change in weight is taken. Sorry, weight is taken on the x-axis. We will take the temperature. As the temperature changes, the weight of the sample changes. So we will record by using the recorder. Okay. So TGA of calcium oxalate monohydrate. Let us see the TGA of thermogravimetric analysis of calcium oxalate monohydrate. Let us see CaC2O4 H2O. Okay, the successive plateau corresponds in the formation of anhydrous salts, calcium carbonate, and calcium oxide. So, if you see this one, if you observe this plot between weight and temperature, the successive plot corresponds to the formation of anhydrous salts, calcium carbonate, and calcium oxide. So, the thermogram indicates the loss of water begins at 100 degrees. So, there will be a loss of water in the calcium oxalate monohydrate at this 100 degrees centigrade. 100 degrees centigrade, this calcium oxalate will lose its water and it will form calcium oxalate monohydrate will lose its water and it will be calcium oxalate, that is CaC2O4. And loss of CO at 400 degrees centigrade. And at 400 degrees centigrade, what this calcium oxalate, that is CaC2O4, it will lose the CO. Carbon monoxide it will lose and it will give CaCO3. Okay. And at 680 degrees centigrade, it will lose carbon dioxide again. So there is, if the lose of carbon dioxide happens, then what happens? There will be only CaO will be released. So as the temperature of the calcium oxalate monohydrate is increased, there will be a successive plateaus. We can observe successive plateaus of formation, right? When the when at temperature is at 100 degrees centigrade, this uh, calcium oxalate monohydrate is losing its water, that is water molecule, that is H2O. At again at 400 degrees centigrade, the CaC2O4 is losing its carbon monoxide and it is forming CaCO3. And again at 680 degrees centigrade, what happening? It is losing its CO2 gas, it is losing CO2 gas and it is forming CaO, isn't it? So this is how the reaction happens. If you see further, we can observe here. You can observe here CaC2O4, H2O at 100 degrees, it is losing CaC2O4 plus H2O. H2O as water molecule at 100 degrees centigrade. Here it is losing. After that, it is at 400 degrees centigrade. At 400 degrees centigrade, actually, 400 degrees centigrade, what it is losing is it is losing carbon monoxide. Carbon monoxide it is losing and it is being CaCO. And at 680 degrees centigrade, what's happening? It is losing CO2. It is losing CO2 and becoming CO. Okay. This is the PGA curve of calcium oxalate monohydrate. Okay. You can observe this one. So what are the factors which can affect this TGA curve, TG curve? Let us see. Factors which may affect the TG curves are classified into two main groups. So instrumental factors, sample characteristics. Maybe due to the instrumental factors, it may get a deviation of the curves in the TG, that is thermogravimetry analysis, or due to the sample characteristics also, there may be a deviation, there may be a flaw which can occur, which can affect the TG curve actually. Let us see what are the effects, what are these factors in the instrumental and sample characteristics have. Okay, these instrumental factors are the furnace heating rate, furnace atmosphere. Instrumental factors, what are the factors of instrumental factors which affect the PG curve? Furnace heating rate or furnace, furnace atmosphere. And next one is sample characteristics includes. What are these sample characteristics? Weight of the sample, sample particle size. So for the instrument, there may be a heating rate, furnace heating rate may be a reason, or furnace atmosphere may be a reason. For sample characteristics, uh, the weight of the sample may affect the PG curve or sample particle size may affect the PG curve. Okay, instrumental factors. As we seen, furnace heating rate and furnace atmosphere. What are the furnace heating rate? How they affect? Let us see. The temperature at which the compound or sample decompose depends upon the heating rate. So the sample will decompose depends on the heating rate. How we are applying the heat. If you apply it at high rate, the decomposition of the sample is also high, isn't it? If the heating rate is low, if you apply heat very slowly, there will be a gradual change in the weight, right? If you apply if you apply rapidly, the heat rate may change the temperature. Due to the change in the temperature of the sample, there may be a disintegration or decomposition of the uh, sample will occur. Let us see. The temperature at which the compound or sample decompose depends on heating rate. Depends on heating rate. When the heating rate is high, the decomposition temperature is also high. So when the heating rate is high, the decomposition rate will be also high. The decomposition temperature is also high. The heating rate of 3.5 degrees centigrade per minute is usually recommended for reliable reproducible TGA. So 3.5 degrees centigrade per minute is a usually recommended uh, for the TGA. Okay, for reliable and reproducible TGA. This is the ideal temperature at which heat rate at which it can decompose. It has to be decomposed. That is 3.5 degree centigrade per minute. Okay. Next, coming to furnace atmosphere. The atmosphere inside the furnace surrounding the sample. The atmosphere inside the furnace surrounding the sample has a profound effect on the decomposition temperature of the sample. There will be a furnace, there will be atmosphere around this furnace that affects the most this sample decomposition. Okay. Pure nitrogen gas from a cylinder pass through the furnace, which provides an inert gas. So, as the N2 gas, the pure nitrogen gas uh, from the cylinder passes through the furnace, which provides inert gas. Inert atmosphere may produce through the N2 gas. Okay. Next, going for the sample characteristics. So, weight of the sample, particle size of the sample. These are the two chances of effects which can affect the PG curve. Okay. Weight of the sample first. A small weight of the sample is recommended. Using small weight eliminates the existence of temperature gradient through the sample. Okay. Small weight of the sample is recommended. Using a small weight eliminates the existence of temperature gradient through the sample. So a small weight is ideal to eliminate the existence of the temperature gradient. Okay. Particle size of the sample. The particle size of the sample should be small and uniform. How must be the particle size? It must be small and uniform. The use of large particle of crystal may result in apparent very rapid weight loss during heating. Okay. The particle size of the sample should be small and uniform. Particle size must be small, and also the weight of the sample is also must be small. Okay. Thus, use of large particle or crystal may result in apparent very rapid weight loss during heating. There may be a very rapid weight loss may occur when the particle size is more. Okay. Applications of TG. Let us see what are the applications of this thermogravimetry analysis. From TGA, we can determine the purity and thermal stability of both primary and secondary standards. So we can determine the primary and secondary standards of the purity and thermal stability of these primary and secondary standards of this. Uh, okay, determination of decomposition of complex mixture and decomposition of complex. You can find the decomposition of complex mixtures here. For studying the sublimation behavior of various substances, we can study the sublimation behavior of substances. PGA is used to study the kinetics of the reaction rate constant. It can also study the kinetics of reaction rate constant used in the study of catalyst. So it can be used in the study of catalyst. The change in chemical states of the catalyst may be studied by TGA techniques. So there will be used in the which is used in the study of catalyst. The change in chemical states of the catalyst may be studied by TGA techniques. Zinc chromium oxide, that is zinc chromate, is used as catalyst in the synthesis of methanol. Okay. So these are the applications of TGA. In the uh, in the next in the upcoming one, we are going to discuss about the DSC. Okay. I hope you understood the TGA. So we have seen the applications of TGA. We have seen the instrumentation. We have seen the principle of TGA. Okay? Next, we are going to study about the DSC curve. Let us see what is DSC. So differential scanning calorimetry. This is differential scanning calorimetry is a next topic. This is also one technique to find the uh, characteristics of a sample sample or the specimen which we use. Okay. So coming to the topic. So what is this DSC? The technique differential scanning calorimetry. DSC measures the differential heat flows associated with transitions in substance and reference materials linearly heated at a predetermined rate as a function of time and sample temperature in controlled atmosphere. So, what this differential scanning calorimetry does, it measures the differential heat flows. So there will be transitions in the substances. There occurs some transitions in the substances. We will take two substances, one sample, which we have to find, and we take the reference one, which we know the values of the sample, the values of the material, which we know the reference materials. We will take the reference materials and we will take the sample, which we have to find. So we will measure those differential heat flows. So we will measure the differential heat flows between this reference as well as the sample. Okay. And we'll try to find the graph. We will plot the graph between that heat flow to the function of time function of time. Okay. So here if you see associated with transitions in substance and reference materials linearly heated at a predetermined rate as a function of time and sample temperature in a controlled atmosphere. These measurements provide quantitative and qualitative information about physical and chemical changes that involves endothermic and exothermic processes or changes in heat capacity. So, by using these measurements, these measurements provides this quantitative and qualitative information about the physical and chemical changes. So this involves these measurements involves some endothermic and exothermic processes. So with the heat change in the heat capacity, there will be a plots where we can see the endothermic and exothermic reactions. When the endothermic reactions occurs, there will be raise in the plot, uh, a gradual rise in the plot, and when there is exothermic reaction, we can observe lowering of that plot, that is decrease in the temperature, I think. Sorry, heat flow. Yeah, there will be curves like this. You can observe in the next slides. So, what is differential scanning calorimetry actually? So what it measures the heat flow between the reference and sample, and it will try to and we will try to plot a graph between the heat flow and the change in time. Okay, and there we will observe endothermic and exothermic reactions. When the heat is absorbed by the sample, there will be endothermic reaction occurs. When heat is released by the sample, when the heat flow is given to that, so there will be observed exothermic process. So that process may be plotted on the in the graph, and that will be improved. Let us see. So both in DSA and DTA, this is differential scanning calorimeter, and this is differential temperature analysis. So these are two different techniques. So DSA and DTA sample in reference both are heated or cooled at constant temperature linearly at predetermined rate. So in these two techniques, the sample as well as the reference both will be heated. Okay, both will be heated or cooled at constant temperature. At constant temperature, the sample is cooled and sample is uh, sample is cooled or sample is heated at predetermined rate. During a thermal event in the sample, the system will transfer heat to or from the sample pan to the maintain the same temperature in reference and sample pans. So during this during this thermal event of the sample, what happens that system will transfer heat from the sample pan to the uh, sample pan to the reference pan, and reference pan to the sample pan to maintain the difference same temperatures to maintain the same temperatures of the sample and reference phase. We will find in the DSC also, in the DTA also, we will try to keep the sample and reference frame at equal temperatures. Okay. During thermal event in the sample, the system will transfer uh, heat from the sample pan to the maintain the same temperature in reference and sample pans. And the sample pans. Okay. There are two basic types of DSC instruments. There will be two types of DSC instruments, that is power compensation DSC and heat flux DSC. These are the two types of DSC which we can observe. Both differ fundamentally in their instrumentation. So these four, both power consumption DSC and heat flux DSC, both will be differ with each other fundamentally. Okay. So power compensation DSC. This is the power compensation DSC. Here you can observe, this is the sample pan, this is the reference pan, which are connected to a thermocouple. Both are connected to a thermocouple. The temperature change in these two reference and sample pan is zero. You can observe the temperature change. The change in temperature delta T is taken as zero. These are the individual heaters for sample pan and uh, reference pan. So these heaters are controlled and delta P is there. So inert gas vacuum will be available. With through this inert gas vacuum, we will keep the uh, environment. Sorry, we will keep it non-reactive, so that it is so the inert gas is allowed keep in this to be in this uh, chamber. Okay, so the sample holder is made up of maximum aluminum or platinum fans will be there. These are made of aluminum and platinum fans. So this is power consumption compensation DSC. Sensors will be platinum resistance thermocouples. These thermocouples are platinum resistance thermocouples. Separate sensors and heaters for the sample and reference plane. There will be separate sensors and samples will be there for this sample and reference planes. Furnace will be there. This is the furnace actually. Separate block for sample and reference planes. So for the actually in DTA, what happens? There will be only one furnace will be there, and only they are connected and they are made to keep in the same temperature. But in the DSC, what happens? The chambers will be different, and the heaters are different for sample and reference pans, and they are made to keep at same temperature. Okay, temperature control. Differential thermal power is supplied to the heaters to maintain the temperature of sample and reference at the program value. So differential thermal power is supplied to the heaters to maintain the temperature of the sample and reference at the program. Okay. Power compensated AC. So this is sample, this is reference frame. These are the dual heaters. So these are platinum sensors. So thermocouples. Two control circuits are employed, one for average temperature control, and other for differential temperature control. So two circuits are given. One is for the average temperature and other is for the differential temperature. In average temperature control circuit, electrical signal is proportional to the desired average temperature of the sample and reference holders as a function of time. So average control circuit, electrical signals will be proportional to what? Average temperature of the sample and reference holders. Okay. In differential temperature circuit, sample and reference signals from platinum resistance sensors are fed into differential amplifiers. The amplifier output then adjusts power input into the two furnaces in such a way there is their temperature are kept identical. So in the differential temperature circuits, what happens? The sample and reference signals from the platinum sensors, these platinum sensors are fed to a differential amplifier. So those are fed to a differential amplifier. The output from the amplifier will adjust the power. Okay, power input to the furnaces. There will be a furnaces surrounding the source and that is sample and reference. So by using these platinum sensors, it will sense and it will amplify and it will give signals to the signals to the power input, so that how much power is needed for the each of the sample and reference. So that power is given to the furnace, so that these are heated at one is heated at slow rate, maybe reheated at high rate. If the temperature of the sample is low, it is heated high rate, so that it can be equilibrium with the reference frame. The temperature between this sample and reference is kept identical. Okay, in such a way that their temperature are kept identical. Heat flux DSC. This is another type of DSC, for heat flux DSC. So here in this heat flux DSC, there are heat coils here. You can observe this is a sample pan, this is the reference pan. So there will be chromal wafer here. There are thermocouples here. You can observe the thermocouples. There is inert gas entry. Valve is there, and constant and chromal aluminum wires are there. So sample holder. Let us see the sample holder. Sample holder and reference are connected by a low resistance heat flow path. So here in this one, heat flux DSC, this sample pan and reference pan are connected to a low resistance heat flow path. Aluminum or platinum pans placed on constant and disk. So On the discs, what happens? The constant and discs, what happens? That we will place this aluminum and platinum pans. Sensors, chromal constantine, copper nickel alloy usually consisting of 55% copper and 45% nickel. So this copper nickel alloy, that is constantine, are used as thermocouples, differential heat flow, chromal aluminal thermocouple, sample temperature. For the sample temperature, we will use chromal aluminal thermocouples, and for differential heat flow, we will use chromal constant. Okay. Furnace. If you go for the furnace, one block for both sample and reference cells. So there will be only one block for this block. In the compensated DSC, what happens? We have seen two blocks of furnaces there. Temperature control. The temperature difference between the sample and reference is converted to differential thermal power. The temperature between the sample and reference is converted to differential thermal power. It is converted to the differential thermal power, which is supplied to the heaters. So this will be supplied to the heaters to maintain the temperature of the sample. To maintain the temperature of the samples, these are supplied to the heaters. Okay. Sample and reference at the programmed value. So temperature between the sample and the reference is converted to a differential power, thermal power, which is given to the heaters, and these heaters will maintain the temperature of the sample and reference field. So here, if you see, you can observe the source. This is the reference fan, which are connected to a thermocouple, that is chromal wire. These are connected to each other with a wire, and there is thermoelectric disc. Constantine is there, thermocouples, chromal disc is there, aluminum wire is there. Okay. Heat flow into both sample and reference materials via electrically heated Constantine thermoelectric discs. Okay, this so heat flow will be there between the reference and sample pan via electrically heated Constantine thermoelectric disc. Okay, there will be heat flow. Thermoelectric disc is there, right? Through this disc, there will be connection to the source and reference pan, so that there will be flow of heat from source to reference, reference to source, sample to reference, reference to sample. Sample and reference is placed on constant and disk. Heat is transferred to it. So on the constant and disk only, the sample and reference is placed. Okay. The differential heat flow into two pans is directly proportional to difference in output of two thermocouple junctions. So the differential heat flow into two pans. The differential heat flow into two pans is directly proportional to what? Output of two thermocouple junctions. So output of the two thermocouple junctions is directly proportional to the heat flow of the differential heat flow of two pans. Sample temperature is estimated by chromal aluminal junction under sample disk. So sample temperature will be estimated. Okay. Sample temperature will be estimated by the chromal aluminum junction under sample disk. Sample disk through this it is estimated. Modulated DC. Heating and cell arrangement is same as the heat. This is another type. So heating and cell arrangement is same as in the heat flux DSC. With the help of Fourier transform program, the overall signal is mathematically deconvoluted. So heat and cell arrangement is same in the heat flux DSC. With the help of Fourier transform program, the overall signal is mathematically deconvoluted into two parts. These are convoluted into two parts: a reversing heat flow signal, non-reversing heat flow signal. Usually, step transitions such as glass transition appears only in the reversing heat flow signal, and exothermic or endothermic events may appear in both the signals. So it may appear endothermic or exothermic. Okay. What can DSC measure? What is the significance of this DSC? Let us see. So by using DSC, you can see the glass transitions, melting and boiling points, crystallization time and temperature, percent crystallinity, heats of fusion, specific heat capacity, oxidative thermal stability, rate and degree of pure, reaction kinetics, purity. Okay, what is the significance? It can be helpful in glass transition for the melting and boiling points, crystallization time and temperature. Also, percent crystallinity, heat flow of fusion and reactions, specific heat capacities, oxidative thermal stability, and rate and degree of pure, and also reaction kinetics, and finally purity also can be seen. So this is the DSC thermogram plot between the heat flow and temperature. Here the downward is the endothermic, the upward one is the exothermic, where the sample is absorbing energy and it is uh, releasing it. Sorry, whenever the sample takes the energy heat and releases the energy, this is the exothermic one, and it absorbs it will be endothermic. Okay. This is the plot between this is VSC thermal. Okay. Why purge gas? Purge gas should always be used during DSC experiments. In the DSC experiments, always purge gas inert gas is used. Provides dry inert atmosphere. It provides what? Provides dry inert atmosphere. Ensures even heating. Okay. Helps sweep away any of gases that might be released. So it sweep away any of the gases that might be released. Okay. Nitrogen, most common. Nitrogen is the most common. Increases sensitivity. Typical flow rate of 50 ml per minute is seen. Keeping the DSC cell clean. One of the first steps to ensure good data is to keep the DSC cell clean. The DSC cell must be uh, clean so that we will get the good data. Okay. How to how do DSC cells get dirty? How decomposition samples during DSC runs? If there is decomposition during DSC runs, it might be there. The samples material may be present. Without cleaning, it may be get dirt. Samples spilling out of the pan. If this kind of samples spill out of the plant, it may get dirt. Transfer from bottom to pan. Okay. From bottom to the pan to sensors, it may get dirt. Okay. How to clean DSC clean DSC cells clean. Do not decompose samples in the DSC cell. So we should not decompose the samples in the DSC cell. Run TGA to determine the decomposition temperature. You have to run TGA to decompose the temperature. Stay below that temperature. You have to stay below that temperature. Make sure bottom of pans stay clean. So we have to see the bottom of the pans which must be clean, and we have to ensure that bottoms are clean or not. We have to use the lids. Use hermetic pans if necessary. We have to use the hermetic pans if necessary. Cleaning cells. If the cell gets dirty, you have to clean with the brush. Brush gently both sensors and cells if necessary. Be careful with the thermocouple. Blow out any remaining particles. You have to blow out the any remaining particles which are present in the DSC. So what we have discussed today, we have discussed the differential scanning calorimetry and also thermogravity analysis, thermogravimetric analyzer, isn't it? So in the thermogravimetric analyzer, uh, we have seen that there will be a change in with the change in the temperature, there will be weight change appears so that we can measure the weight of the sample when change in temperature or time. In the scanning calorimetry, we have taken the sample. We have taken a reference one, reference sample, and sorry, reference material, and also sample. So we have we have given temperature to this sample and reference equally, and we have measured the temperature difference between heat flow difference between heat flows between these temperature and sorry reference and sample, and we found the characteristics, right? So we can see the quantitative and qualitative information about this sample by using endothermic and exothermic reactions. Okay, and we have seen some DSC curves here. This is the these are the two. So there are two types of DSC. The one is compensation DSC. Another one is heat flux DSC. In the power compensation DSC, the sample and reference plants are having two different furnaces, two individual heaters for both the samples and sample and reference point, and also individual thermocouples are also there. The sample and reference point. But and also they have given the inert gas, and for the heat flux DSC, we don't have two furnaces. We only have one furnace, but this sample pan and reference pan are connected with each other um, through a low resistance wire. Okay, through a low resistance heat flow path. So in the power compensator DSC, what happens? You will see the by using the sensors, you will see the temperature difference or the heat flow temperature difference between the source and reference, and we will try to give through the amplifier to the heat flow system, and the heat flow to the furnace is given where the temperature to keep the temperature of the sample and reference. Okay, so this is about heat flux DSC and power compensated DSC. So what is the significance of DSC? It is used in the glass transitions, melting and boiling points, and it is DSC is also used to find the find in the to find the polymers characteristics. We can find the melting and boiling points, and also in nanotechnology, nanomaterials also it can be used, and also it can be used for dating purpose in the archaeology. Okay, so this is the DSC thermograph. You can observe here. This is the DSC thermograph. So this is thank you. In the next class, we are going to discuss other techniques which are used for the material characteristics. We will do the resonance spectroscopy, but also Mazuber effect. Okay, theory of Mazuber effect. We will try to see. Okay, thank you. Thank you for this opportunity.